Damien, I think you're going to be talking about some of the newer features that have gone in since last time we met, really.
Yep. Oh, yep.
Cool.
Should I go? Are you
Just
ready?
dive straight into it. Thanks, Damien. People are listening.
All right. Hi everyone, and well, we had a nice break over the new year. There was, I think, maybe 2 or even 3 weeks where there was no activity, which was a good break for me and hopefully other people. There was a bit of activity over that time, but I think a lot of people had a break. And since the start of the new year, Jim and I have been trying very hard to reduce the number of pull requests. The idea is to get that down to close to zero this first half of this year, hopefully. It was down to almost 240 the other day, but it's gone back up a little bit. But yep, we're making a concerted effort to get that down. And also, I know that a release has not been made in a long time. That's also on the top of the agenda. There's just a few things with the RP2 port that are holding that up. And once that's done, there should be a release in the next couple of weeks. So I was just going to go through, well, yeah, a few things that were done, merged in the past since the start of the year, and also then talk a little bit about compression support, which a few people have been asking for, and there's a couple of pull requests for that. And I'll talk a bit about how we're going to get that in, because compression is not easy with little resources. So I'll need to share my screen first before I do that bit. No, desktop one. Can you see text? So one of the things that was fixed at the end of last year was open networks, Wi-Fi networks with open security on RP 2040. So that should now work. That has been working since the start, but it is now fixed. The other thing on the RP 2040 port was to improve PWM. So there's a bit more accuracy in calculating the frequency and duty there. Which is useful. Lots of other little things have gone in. I'm definitely not going to go through these all these commits here, but fixes like this one for USB on startup of RP 2040, docs improvements, and then Ibrahim's work on named pins for the RP2 port has gone in now. So like it is with STM32 and PyBoard, you can now use names for your pins. And some boards have already got their names in there, but new ones need to be added. For example, this Arduino Nano RP2040 Connect, the pins as they are named on the silk screen can now be used to construct a pin like TX. Or D10 or LED, LEDR, even LED. So that's good because that brings it in line with STM32, and hopefully the other ports can use the same code. I think also MIMAXRT has this as well, and maybe even SAMD now. But the aim is to unify all this so everything works the same, and this is a good step. I think the only main port that doesn't have this now is ESP32. So as I said, lots of minor fixes. Support now for named classes in regular expressions. There were a few bug reports on that recently. So basically, you can now use like \w, \s, \d within a character class within square brackets. So that's useful. ESP32 has a few new LAN features, extra PHYs supported, supporting refclock pin, and SPI-based Ethernet chips. So ESP32 with like a WISnet 5500, for example. So there's that's all this stuff's been contributed by other people, which is great. People who need this feature, and it seems good to support it because it's part of the IDF anyway. So networking with wired LAN is now better on ESP32. Yeah, fixes, improvements, lots of small things here and there. A unicore ESP32 board definition, if that's needed. More LAN PHY things. There was one bug fixes there, and yeah, that's about all. Another bug fix on RP2040 for the open drain pins. So just bits and pieces here, trying to clean up things before we make a release. As I said, though, one of the things that had been requested is a compression, and there are, let me have a look. There's a couple of pull requests and issues dedicated to this, people contributing compression support in the UZlib library. Now, compression is we have decompression supported in MicroPython, which has been there since very early days, and that works. But compression is harder because you have to do a bit more work, and you also need quite a lot of memory to compress things. So I'll just give a really sort of brief overview of how compression works for a for LZ77, which is the format that's used. This is a slide from someone's YouTube talk that I've taken here. You can see the address if you want to go. But it's explaining how when you compress something using LZ77, how that's actually done. So the main technique here is dictionary compression. So you look back in your stream of data to see if the same pattern has been before, and if it has, you refer to that previous pattern rather than store it again. So if you're storing a long string of English text, for example, then the word "the" appears quite often. Instead of having four characters, THE plus a space, for every time you get "the," you can just say, oh, look back in the stream to position 200 and copy 4 bytes, and that'll just be the "the" that you copy. And it's usually more efficient to say look back in the stream and copy bytes than it is to actually write those bytes literally. So here on this diagram is depicting that. So the first few characters, obviously, you don't have any previous history, so you've got to store them as they are. So here A is stored, then B, and then R. And then the next thing you want to encode is A and C, and you've already seen an A. So this tuple on the left is saying look back 3 characters and copy 1 character, and then add a C. And then you keep doing that, and by the time you've got to the bit here, A, B, R, A, R, you can look back 7 characters and copy 4 because you've already seen A, B, R, A before at the very start of the string. So you can see how the more you get into the string, you can look back and use your essentially a dictionary of things that you've seen to encode to compress the stream. So that's the first part of compression. The second part is then encoding these tuples on the left, these 3 tuples, efficiently encoding them. And that's done using a Huffman compression where the most common things are stored with fewer bits. So I won't really explain how that works. But the reason to sort of understand this dictionary, this look back technique, is because it requires quite a lot of memory to store that history that you have, and to then search in that history. So there's 2 things there that are not abundant on microcontrollers, which is memory storage and processing power. So if you have a really big history, so usually it's 32K, so you have 32K byte buffer of history of what you've stored in the stream. You need the RAM to store that, and then every time you come up to a new set of characters to encode, to compress, you have to go and look back in that 32K to find the same pattern. And looking in 32 kilobytes, searching that is also quite slow. So what you have to do is actually create a hash table indexing that history. So not only do you have 32 kilobytes of history, you also have quite a large dictionary or a hash table, which says, you know, if your next string starts with an A, you should look here in the history. If the next string starts with a B, you should look here, and so on. It makes it quicker to search the history, but it also means you need to have a very big hash table, basically, you know, a pointer for each byte plus, well, other things. And so that's all. It's almost doubles the memory usage that you need to compress. So already you need maybe 64 kilobytes of RAM to do compression plus, well, if you do it that way, the processing power is lower. You don't need that you don't need that dictionary and that hash table if you don't want to. That's just there for an optimization of speed. But if you don't have it, it's very, very, very slow to search in 32K of history. So, well, you have to make some trade-offs here, because obviously you cannot do this on a microcontroller. There's this pull request here which builds on another one by Andrew, the first one, Andrew Leach, that is. So this is a simple implementation of compress, and you can see here how much memory it's allocating. So just in this line here of GC alloc, it has to allocate here the hash table, hash size, and hash size is 1 to the power of hash bits, and hash bits is 12. So you're allocating a 4096 entry table here, and each entry, I think this is a pointer, so it's another 4 bytes. So 4 bytes times 4 kilobytes is 16 kilobytes of RAM. So this allocation here is 16 kilobytes big. And then you can see here the dictionary is also set to 32K. You don't actually allocate anything for that dictionary, because this function actually just compresses its string in, well, it just takes a big string and compresses it. So the history is just the string that's there already somewhere. So this function here, as it currently stands, needs to allocate about 16 kilobytes of RAM to compress any string, even if the string is only 10 bytes long. And it's fast because it uses this dictionary lookup, but obviously uses lots of memory. And if you wanted, so this also, as I said, it just takes a given block of data and compresses it. If you want to compress a stream, so say you have a large file that you want to compress, or not that large, but a log file that you can't load into memory because it's too big, you need to have a streaming compressor, and this one here is not a streaming compressor. To have a streaming compressor, you need to have history, so you'll need to allocate 32K of RAM as well to store all the data as it's being streamed from the raw data to the compressed data. So you can see that there are obviously things here we have to trade off. So this function here, as it's written, it says, okay, we need to use 16K of RAM, and we can only compress things that are already given to us, and then it will work. I don't think this is a good, well, the reason I haven't merged this pull request is because I don't think this is a good trade-off for a microcontroller. So the implementation that I have, which is not yet a pull request, but I'm getting it ready to make a pull request. So the same compression function doesn't actually allocate any memory. It doesn't have any, the history is just the data that you're compressing, and there's no dictionary or hash table to index that history. It just does a brute force linear search. And to keep that not too slow, it only looks back configurably, but by default 256 bytes. So the history window is only 256 bytes, not 32K. And then if it's that small, doing just a brute force search every time you're looking for something, it's actually not that slow. And surprisingly, a 256 byte history also gives you decent compression rate. So you can play off all these parameters. bigger history gives you better compression, but then you need more memory to index it and to make it fast. So there's sort of compression rate, memory usage, and speed of compression are the three things you have to decide on your compromise. And so the implementation I have here is, well, minimal memory, because in this case it uses 0 extra RAM to do the compression, except for the input buffer and the output buffer, but you'll always need that. Decent compression ratio and relatively okay speed. It also supports streaming, and when you have it streaming, you only need an extra 256 bytes of RAM to store the actual history as the data comes in and gets stored in a buffer. So this is the implementation that I've come up with, and I've tested it quite a bit in terms of performance and compression ratio, and I'll give some numbers when I make a pull request to compare. But I'd much rather see this kind of implementation that has these trade-offs, because I think they're more useful in a setting for a microcontroller. So because usually, well, you might have a small string that you want to compress, and in that case it's not going to be very slow to compress because it's very small, and the history is always going to be tiny. If you've only got a 100-byte string, it'll only ever have a maximum of 100-byte history. If you've got a big log file that you want to compress, then you definitely want to do streaming. And yeah, if you want to have better compression, you can just increase the window size at the expense of speed. So that's sort of a brief summary of the situation with compression. And hopefully from it, you can appreciate that it's not obvious, or there's no one correct answer as to, yes, let's just implement compression on a microcontroller. There are trade-offs to be made. And the good thing with LZ77 compression is that you do have these parameters that you to tune. You don't have to have a buffer of 32K, and you don't have to have a dictionary at all. There are different ways of doing the same thing, and the output is still going to be the same. So in this test file that I have here, you can see some example strings. So if the input word is hello, then this is the compressed stream. It's bigger than hello. That's because there's not much to compress, but it just gives you an example. And then there are 3 ways that you can format that compressed data. There's a raw, which just leaves it as it is. There's zlib format, which adds a 2-byte header and a 4-byte checksum at the end, an Adler32 checksum. And then the one that's a bit more common is gzip, which adds, I think, a 10-byte header at minimum. It could be more, but 10 is the minimum, and an 8-byte trailer, which is a CSE32 and a length. But otherwise, the internal data is the same on all 3 of these compression sort of formats. And CPython supports all 3 of these in its zlib module, so we do as well. So that's sort of a summary. I think the final thing to say is that there's actually a gzip module, not zlib. So zlib is the one we already have, but there's also a gzip module in CPython, which has a gzip file class. And Jim and I were discussing this, and we think perhaps it's better to implement that rather than zlib.compress. Well, actually, we'll implement zlib.compress as well, but for streaming compression, I think gzip file is probably the way to go, because most people want to just compress gzip, and that also supports decompression. So this is sort of the roadmap or ideas for compression, because I know that lots of people have been asking about it, and the code's there. It just needs to be put in a format that can be mergeable. So I'll make a pull request with the code that you see here, and some more statistics and data on how it compresses, and then we can, well, make a decision. So that's once we've done that, then we'll be able to close a few more pull requests, which will be good. But hopefully you can appreciate that it's a lot of work to a pull request like this. It's not just, yes, that's nice, let's merge it, or here's a few comments. Sometimes it's like, no, this is not the right scheme. we need to do it a different way, and take some time to go through that. So I think that's all I have to say about the commits that have been in and compression support. Yeah, I think if there's any questions about what I've said, feel free to ask.